Yeah, if you haven't done so, please just type in hello in the chat box so that I know you are present and all that. And also, the lectures would be recorded. Thanks, Josh. I have made last year's lectures available anyway. Those are on the LMS page, and you can have a look at them as well. Recording may not be that great for last year lectures because those were echo recorded, only the slides and my voice, no face-to-face videos. Anyway, let me press the record button and then we would start. All right, welcome to Discrete Mathematics, everyone. In this subject, okay, let me go over the LMS page first. You can see learning management system page that I shared with you. And I have taken the student view there. If you see up there on the right-hand corner, these are all the things that you can see as well. So may I, okay, what I would like to go over, now, firstly, I would explain this LMS page and what resources you have. And then I will go over the subject learning guide and then the lecture. Okay, the first thing that you will see about this subject is the subject learning guide. I won't click it at this time. I will do that later. But what I would like you to do later, today or tomorrow, is to watch this video and understand it. There is actually, we have taken really a hard stance on cheating and copying and all that. And you should be familiar with what is contract cheating, what is collusion, what is cheating, and those kind of things. So at any stage, we don't want you to actually, if you copy from somewhere, you have to acknowledge it, state it, and there's basically in certain essays when you write, which are basically, we don't do that in discrete math that much. They are just formal questions and all that. And if you take help for formal assessments, that may be counted towards cheating. All right. So all the work should be entirely of your own. Okay, well, I have put these two links here. We will be meeting on Wednesday, 12 o'clock to 1 o'clock. That would be our lecture 1. 1 o'clock to 2 o'clock is tutorial. That will start from week 2. So not today. All right. On Friday, we have 2 lectures, 10 to 11 and then 11 to 12. What I did, I made this folder here, Zoom recorded lectures. So what I'm going to do, I'm going to record every lecture and put a video in this folder. However, if you see on the right-hand side, there is this Echo 360. If you click on it, which I'm doing now, what you're going to see, you're going to see all the recorded lectures which were done last year. So starting from August 5 and then 6 and 6 and all that. So all of these lectures are recorded. So apart from the first lecture, where there is actually the video was not captured, only my voice is there. Apart from the first lecture, all other lectures are complete. They are fully recorded. The best to the facility we had, right? But I personally like to give synchronous lectures. That means live lectures, so that you have the opportunity to ask me questions at any stage. Right? Okay, so that resource is there for you. Then what I did, I have uploaded all the PDFs, I mean lecture slides, split into weekly sections. So this is week 12, then week 11, up to so on. So you will be starting from week 1 here, where lecture 1 is at the bottom. So lecture 1, decimal and binary number system, that I would go today. I'll cover that today. So it is there, and then lecture 2 and lecture 3. So if you click in on it, you will see the entire PDF of what we have covered. So that resource is there for you. So what I did, why I made all the lectures available right at start, because some students, they want to see that what we're going to cover in the next week or the week after, things like that. Or some students, you know, they want to see the complete picture, right? So it's there for you. Then what's next? After that, we have tutorial resources. Tutorial means practice classes, problem sessions, and all that. So there are problems here that I have, as you can see, discrete mathematics. So these problems are taken from Peter Grossman's discrete math book. I would share those problems with you in a minute. So here is the, for example, I have scanned that book and put the questions there. All of them, and similarly, alongside questions, there are solutions as well. Okay, so some extended solutions and all that, those are also provided. Until last year, there are 3 assessments. Okay, still in this year as well, there are 3 assessments in this subject. Assessment 1 used to be assessment 1 and 2 used to be 2 tests, in-class tests, but since we are not going back to face-to-face teaching on campus yet, so I have replaced those in-class tests with an assignment. So in week 5, we will have an assignment, and then in week 9, we would have a test that I will conduct online with you. So assignment would be 15%, I mean 15 marks. Test would be 20%, 20 marks, and the final exam would be 65% of total. What I did, I have provided test 1 that used to be in the previous years with its solutions, and test 2 with its solutions as well, so that you can see the structure of tests and what kind of questions we ask. As well as I have provided all the exams, previous exams with solutions. So as far as the resources are concerned, there are plenty here, and that should be enough for you to, you know, to understand this entire subject. However, if you want more resources, more like learning material, I mean, you can Google any topic and you will get lots and lots of things, or just ask me. I would guide you on that. Now, the most important document that I would like you to go over is this subject learning guide. It gives you every information that you need to know. Okay. So starting with what the subject is, it is 15 credit points. It will be online with you the way we are doing. Ways of communication, you can contact me by dialing this number. I can still attend calls on that, as well as you can contact me through this Zoom ID, but it is by appointment only. So my preferred method of contact is by email. If you send me an email, normally I respond emails immediately. But if I forget to respond to your email in a day, please do nag me, so I will get back to you straight away. Those who has studied, who's taken subjects with me previously, they know that, okay, I'm normally efficient in responding emails and responding queries straight away. All right, okay. Well, I have formal consultation slots as well, and I will definitely be available. You don't need an appointment on these times, so you just walk in. What you do, by walk-in, I mean type in this Zoom ID, and you will be direct to me, and we can do the consultation. Please go over, read through the subject, intended learning outcomes and all that. Okay, and here is the assessment task. 15% for the assignment, 20% for the test, and then 60% for the final exam. The textbook that I'm recommending is Discrete Mathematics for Computing. If you can get a PDF copy, good. If you don't have it, don't worry about it, because I have written lecture notes comprehensively. All the lecturing material slides are up there, on LMS. So you don't really have to buy a book. But if you buy that's also a good one. There are also actually a few other free books available on, if you search them up, there are lots of free books you can have. So yeah, so it's your choice what you want to do. All right, okay, well, yeah, this is what we have. If you have any question, you can ask me now, and I would be happy to answer your questions before the start of the lecture. Yeah, my name is Mumtaz Hussain, and well, what else? Well, I did my PhD from the University of York in England in 2010, towards the end of 2010. And what I did afterwards, yes. After that, I spent a year or some time in Denmark on a postdoc. Then I was at the University of Newcastle on a postdoc. Then I was on a fellowship at Boston, Brandeis University in US. And then I came to La Trobe. Yeah. All right. My area of expertise, I would say my area of research is number theory. You would get a taste of number theory in this subject as well. Well, I would, I'll talk about that when it comes to it. As well as with number theory, I do research in dynamics as well. What else? Yeah, these are, that's my background. If you want to know more, yeah, please feel free. Yeah.
Sorry, Mumtaz, are you based in Bendigo or?
Yes, I'm in Bendigo, yes. Yeah. We normally used to give these lectures face-to-face, and I thoroughly enjoy that. But of course, now we are not in that luxury anymore at this stage. Yeah.
Are the tests and exams open book, or?
Those would be, I will explain them close to that point. Assignment will be open book, of course, whatever you can do. Test, most likely not. Previously, it was in-class test only. That means in the 50 minutes, you are not allowed to have any material except one A4 handwritten formula sheet that you can have. But this year I will modify that slightly now. Modify the test, and yeah. So I'm not fully actually, I haven't made a decision yet what kind of test I really want to have. You know. Anyone else? Any questions? All right. Okay. If none, look, in this lecture, in this subject overall, there are 6 topics that we want to cover. The topics are number bases and computer representation of numbers. And the second topic that we will do is logic. Just one second. Sorry, I have to make things around so that I'm looking at you, not on other screen where my slides are. Okay. Well, as I said, there are 6 topics. Number basis, computer representation of numbers. Logic is topic 2. Third one would be sets and relations. Fourth, sequences and recursion. Fifth, Boolean algebra and digital circuits. And 6th would be cryptography. Well, in all of these topics, what we are doing, we are actually what we are looking at how numbers are stored in computer, and how we type. If we type in a phrase or a statement, true or false, whatever forms that we want to have, how it's being stored in computer, how arithmetic has been done, things like that. You know, it would be a gentle introduction to our understanding of how computers work or how they interpret our daily statements. Okay, so starting with the real numbers, numbers and bases. So we would start with firstly real numbers and the decimal number system. So I would take the introduction back to the school days where you first time started studying numbers. And there you studied real numbers. These are the numbers that you use in daily life, like 1, 2, 3, and then numbers between 1 and 2, which could be 1.1, 1.2, fractions and all that. So any number that you use in daily life is a real number. And amongst them, important types of real numbers are natural numbers, for instance. These are counting numbers, 1, 2, 3, 4, 5, 6, so on, up to that. And then integers. Integers are the numbers if you count their, if you consider the negative halves of natural numbers as well, then those numbers are named as integers. Then we have rational numbers. Rational numbers, all those numbers which you can write in fraction form. Fraction form means like a ratio of 2 integers, right? So these include, let me put some examples here. 2 divided by 5, for example, which is like 0.4, is a rational number. Negative 13 over 72 is a rational number. And 2.25 or 2 1/4 is also a rational number. So similarly, there are many, many, many rational numbers. Can I ask you, how many rational numbers are there? I feel just think. Imagine, how many rational numbers are there?
Infinite.
Infinite, yeah.
Fantastic. Yeah. Okay, good. All right. Okay. Hang in there. I would ask slightly more questions. Yeah. Note that these integers are also rational numbers because you can write negative 3 divided by 1, for example, or negative 6 divided by 2 to make it negative 3. So all of those integers are rational numbers. Natural numbers are rational numbers and all that. Okay. Numbers which are not rational are called irrational numbers. Now, can you give me examples of irrational numbers?
Pi.
Wow, good. Any other? Right,
Well, the next slide, you've got square roots. So I guess those.
Square root 2, square root 3. How about square root 4? Is that an irrational number?
No.
No.
No. This is definitely not. Square root 5, so on. Okay. Now, well, this number look a bit odd here, right? Don't you think? I mean, you can see there's a 2, 3, 4, 5, so on, which are sort of algebraic numbers. Algebraic means solution of an equation. For example, square root 2 is a solution of x squared minus 2 is equals to 0, right? Okay. So this implies x is equals to, sorry about my handwriting here. So this implies x is equals to plus minus square root 2. So fine. But where this pi fits in? Look, this is just a philosophical discussion at this time. It does not have much to do with the subject at this stage. I just want to explore this. I just want to encourage the thinking habit and question your understanding at every stage, that how much we know about things. So pi, you say that it's an irrational number. Let me go, yes, it is irrational number, but let me give you more information about that. It's actually more than that. It is a transcendental number. Transcendental numbers, a number that transcend on us. It is not a solution of any equation, but it's a transcendental, it just transcend on us. It's not a consequence of solving this kind of equations. It just appeared. Okay. There are other numbers like e, like log, and many other those kind of numbers which are transcendental numbers. These are all irrational numbers. Now, naturally, you want to ask, okay, there are rational numbers and there are irrational numbers. Now, can you tell me, think of that, which numbers are bigger than, which numbers are more than the other? Are irrational numbers more than rational numbers, or rational numbers are more than irrational numbers? It's not a trick question, no, it's a genuine question.
I think there'd be more rational numbers.
Mm-hmm. There are more rational numbers. So let me call rational numbers as Q and irrational numbers as Q star. Yeah. So some of you would think that rational numbers are more than irrational numbers, but it is actually not true. Irrational numbers are way, way more, cardinality of it is, irrational numbers are way, way more than rational numbers. Numbers of this kind, square root 2, square root 3, e, pi, log, and all that, they are way, way more than rational numbers. One way of understanding them is that the rational numbers are countable. Like you can say, okay, you can associate each rational number with sort of natural numbers or their ratios or all that, or pair. And that means you can, in other words, count them. So these are countable. However, irrational numbers, you cannot count them. They are uncountable. So they're way, way too many. Okay. So yeah. So yeah, sure. No, there is one infinity could be bigger than the other infinity. In terms of counting, this is infinity, way more than infinity actually. This is also infinite, but countable, like 1, 2, 3, 4, 5, 6, so on. You can count them. This is so much infinite that you even cannot count them. These are uncountable. Okay. However, as far as your computer is concerned and all that, everything is stored as a concatenation, as a count, as a rational number. So up to certain like billion decimals, but then you concatenate it, you stop it. For example, if you go 1.2, 3, 4, 5, blah, 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 up to so on billion digits, but then you have to stop it at some stage to feed the number in. For irrational numbers, these numbers, they never stop. They just keep going. Their decimal expansion just keep going forever. All right. So this brings us to the to a bit more about this. So what are rational and what are irrational? Every rational number can be written as either a terminating decimal or a recurring decimal. So we are looking at the type of rational numbers. So examples would include like 1/3, 1.75. So it's a terminating decimal, means the decimal has stopped here. Okay. And then 2/3, for example, 0.66666. So this is a recurring decimal. That means 6 or a block of digits repeat themselves periodically. If certain digits repeat themselves periodically, then the number is rational. We are at the moment trying to characterize what the rational numbers are, and then we will characterize what the irrational numbers are. Okay, so 2/7, for example, it's 0.285714, 285714. So 28, this block repeats itself indefinitely, right? So when there is a repetition or periodicity, that number is rational. Okay. And similarly, after this, it is 25, 25, 25, 25, 25. So that's also rational number. If these characteristics or attributes don't appear in a number, then that number would be irrational. So irrational examples are, as you can see, 0.10, 100, 1000, 140, and so on. So as you can see, there is no periodicity. So a block is not repeating itself after certain instances, right? So there is no repetition. So this number is irrational. Okay. There is a specific name for this kind of numbers. Those are called actually Liouville numbers. You don't really have to know. It's just out of curiosity. I'm telling you that okay, these are the names of these numbers. Similarly, square root 2 is 1.4142135623730. As you can see, no block of digits is repeating themselves. So it's a non-recurring decimal. So non-recurring, non-terminating decimal. So such numbers are called irrational numbers. Okay. Pi has significant importance for us. As you know, still we are trying to understand pi, and up to trillion, up to many actually digits we know, but we still don't know their exact patterns. I mean, how many times digit 1 would appear in those expansions, how many times digit 2 would appear, and things like that. Anyway, that's also an irrational number. Any questions, anyone? So far, any questions? Okay, so if none, well, we start with place values and base. In a decimal number such as 6,245.37, each digit has a place value, and that depends on its position in relation to this decimal point. Okay, so we can write this number as there are 6 thousands here, there are 2 hundreds, there are 4 tens, and 5 units. Okay. This way of writing is extremely important for us because we want to understand these expansions in for the computer binary system. So, okay, so the place value means where these numbers are appearing, like 6,245 means there are 6,000s, 200s, 4 tens, and 5 units, 3 tenth fractions, and 700th fractions there, right? So in other words, you can write this number as 6 times 10 cubed. There are 3 zeros in 1,000. This 100 can be written as 10 squared. 10 can be written as 10 to power 1. 1 can be written as 10 to power 0. This 1 over 10 can be written as 10 to power negative 1. And 1 over 100 can be written as 10 to power negative 2. A natural question here, which I would like to encourage you all to think, is that at every stage, if I've used certain fact, a certain truth, a certain value, you have to question yourself that why. For example, why you think I wrote 10 to power 0 is 1?
Because 10 to the power 0 is 1.
Why?
That's what it is.
Look, in mathematics, there are certain facts that we know, but those facts are derived based on certain logic, certain expressions, right? There is always logic behind it. There are always mathematical proofs behind them. So what I want to ask you and encourage you actually to think every time, if I'm writing or quoting a fact, then you have to question that why that is true, okay? So remember, we have, if I have A divided by A, okay, that would be equals to 1, right? Or in other words, if I would say that, okay, 10 split into 10 people would be 1 each, right? Right. Okay. Or 10 to power 2, 100 divided by 100 is also 1. In other words, if there are 100 units of things and you want to give that to 100, let's say you want to split them into 100 parts, then there would be 1 part each, right? So this factor can be written as 10 to power 2 multiplied by 10 to power minus 2. You take that to numerator, which is basically 2 minus 2, which is 10 to power 0. So 10 to power 0 is actually 1. I should have, yeah, okay. So that's why if you have any non-zero quantity like A, its power 0 would be 1, where A is not equals to 0. So natural question is what happens when A is 0, right? So you think about that, okay. I move forward then. So here the place values are powers of 10. We say that the decimal system has base 10. So if you're writing numbers in this format, 10 to cube, 10 squared, 10 to power 1, 0, these are bases, right? This is a base 10 system that we work in. So all of our counting that happens in daily life is in base 10 system, right? And in base 10 system, there are 10 digits that we deal with. Those 10 digits are 1, 2, 3, 4, 5, 6, 7, 8, and 9. And what would be the next? 0. So these 0 to 9 digits, all of them combine, this makes this base 10 system. Yeah. So these are our daily life expressions and everything that we do. Again, you can think of yourself why, well, yeah, this is, okay. It's just out of curiosity, why we came up with just 10 digits? Why not, let's say 16 or 20 or 25 or something like that, that kind of base? Why we just satisfied with the 10 base system? Oh, fantastic, Josh. That's a very good answer. Exactly. Look, it's a human instinct. We had these fingers. We have 10 fingers, right? And we can that's why one of the reasons that we are used to of counting them 1, 2, 3 like that, and we stopped with 10 different digits. If humans had, let's say, 12 fingers altogether, everyone had 12 fingers, then we might have like 12 different digits to work with. Well, there was actually 8-number system as well, where people were not counting thumbs; they were only counting fingers. And to a certain extent, they were satisfied with 8-base system, and that worked well as well.
Is there a 20-base system if they included toes?
We can come up with that as well. We can do that, yes. It's just out of curiosity. Well, this inclusion of 0 actually in human history came quite late. Yeah, so that's a different discussion. Maybe I put that off to some other time. Let's move on to our study. What we want to do, we want to study the binary number system. In certain sense, binary number system is a lot easier than the 10-digit system. Why we might think otherwise, that 10-digit system is easier than the binary, but if you think closely, you would see that we consider decimal number system like 10-digit system is easier because we are used to of that. It's just a matter of getting used to of numbers, all right? Once you're used to of something, then you find that thing slightly easier than the other. Okay, what is binary number system? This is the simplest number system. Is like base 2. Base 2 means you are only allowed 2 digits in it, either 0 or 1. Okay, and these are known as bits, which are short for binary. BI comes from here, and ITS comes from digits to make it bits. Binary is used exclusively within computers. Each memory element can be in one of only 2 states, that is magnetized or unmagnetized, or on or off. If 0 is off, then 1 is on, or vice versa. Okay, so there are only 2 options, right or wrong, true or false, on or off, magnetized or unmagnetized. So in certain sense, if you're only allowed digits 0 and 1, things are a lot simpler. Okay, in base 10 system, you have 1, 0, 1, 2, 3, 4, up to so on 9. So there are 10 numbers you're dealing with. Here you're only dealing with 2. So 2 is a lot simpler than 10. Yeah. So a typical binary number is 1011.101. So this 2 indicates that it is written in binary. So this number has certain meanings. All right? If we want to understand that, what this number represents in the decimals, we can do that. All right. So whenever we are writing a different base than 10, we have to include that base number small there to indicate that's base 2. Okay, to distinguish it from other numbers. Now, if we want to understand that what this number actually represents in the decimal, then we need to understand the place values. Remember the place values that we did for that 6,245.37 number. Yeah. So we want to convert 1011.101 to the base 2 to decimal. When I say decimal, I mean a real number that we are familiar with, or up to which has 10 digits in it. Okay, so the conversion methods are are based on, again, the place value that we have learned. So we expand this number in powers of 2. Okay. So in order to expand this number in powers of 2, we would have, remember, this one would be 1 times 2 to power 0 plus 1 times 2 to power 1 plus 0 times 2 to power 2 plus 1 times 2 to power 3. So 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. All right. And similarly on the fractional sides, so let me erase this so that I can move on to this slide. Here is in a detailed form. So this 1 times 2 to power 3, that's 0, 0 times 2 to power 2. That 1 is 1 times 2 to power 1, and this one is 1 times 2 to power 0. And after decimals, we'll go in the negative powers. So 1 times 2 to power minus 1, 0 times 2 to power minus 2, and 1 times 2 to power minus 3. So this brings us, then we can calculate them. 1 times 2 to power 3 means 2 is multiplied to itself 3 times. That would be 8. This 0 times 4 is 0. 1 times 2 is 2. And now 2 to power 0 is 1. So 1 times 1 is 1. And then the fractions would be simply 1 times 1 over 2 would be simply 0.5. 1 over 2 to power 3 would be 0.125, and so on. And what you do then, you simply add all of these numbers up. And when you add all of them up, your answer is 11.625. So in other words, 1011.101 to the base 2 is actually a number 11.625. So roughly speaking, if you type in on your keyboard 11.625, that would be read as 1011.102 internally by the computer. Okay. Everything in the circuits and all that, it's being stored in terms of these bits. Any questions? Anyone so far? Okay. So this is how we convert from binary to decimal, and then another example: convert 110001.0112 to decimal. If I want to do that, okay, I would start with the first number. Here I can start from here, and 1 times 2 to power 0 plus, now for this 0, okay, that would be 0 times 2 to power 1 plus 0 times 2 to power 2 plus 0 times 2 to power 3. So all these zeros are covered, plus 1 times 2 to power 4 plus 1 times 2 to power 5. On the then other decimal side, 0 times 2 to power minus 1 plus 1 times 2 to power minus 2 plus 1 times 2 to power minus 3. So now throughout all of these calculations, you would see that there would be multiplications involved, and these multiplications would become bigger and bigger at the later stage of this subject, when we'll be dealing with higher bases. Like at the moment we're dealing with binary, but later we will be dealing with octal and hexadecimal, bases and all that. And then there will be higher and higher powers involved, so you would have to multiply them slightly quickly. So 2 to power 5 means 2, 4, 8, 16, 32. So you write 32 plus 1 times 2 to power 4 is 16 plus 0 plus 0 plus 0 plus 1 times 2 to power 0 is 1 plus 0 plus 1 over 4 is 0.25 plus 1 over 8 is 0.125. So that would be equals to 48, 49, and that would be equals to 49 point, oh, what happened? 49 point, now you add them up and you would have 375. So this big number in binary is equals to 49.375 in decimal representation. Any questions, anyone? Right. Okay, so 49.375 is the answer for this question, and there are similarly many other questions we may ask. Now, next question is converting decimal to binary. So far, we converted binary to decimal, and we just wrote them in their place values. Now, if we have a decimal number and we want to convert that into binary, then how we would proceed? So the first step that I'm going to do, I just want to convert an integer number, right? A number, a whole number into binary, and see how we do that. So firstly, we deal with convert 183 to binary. Okay, there are two ways you can think of. You can think of writing them in terms of 2 to powers. That's one way. Or second way is simply divide them by 2. So okay, let me explain the first method. So the powers of 2 are 2 to power 0 is 1, 2 to power 1 is 2, 2 to power 2 is 4, then 8, 16, 32. So this is 2 to power 0, 1, 2, 3, 4, 5, 6, 7, so on. Yeah. So you can write 183 as 128, which is 2 to power 7. Okay. Plus, remember I said there are more than one method to write this representation, so I'm explaining just one method at the moment. So 128 plus what power I can use from here. If I add 64, this number will go 192, which is more than 183. So I would then put 32. So 128 plus 32 is 160. Then I can have 16, that make 176. Then I can have 4, that will make 180, then 2, then 1. So as you can see, 128 plus 32 is 160, 176, 180, 182, 183. So all of these numbers are written as powers of 2, right? So this 128 can be written as it's 2 to power 7, 2 to power 5, 2 to power 4, 2 to power 2, 2 to power 1, and 2 to power 0. So what these numbers are then, 2 to power 7 means 1, and then there are 7 zeros in it. Yeah. 2 to power 5 means 1, and then there are 5 zeros in it. 2 to power 4 means 1, and there are 4 zeros in it. Similarly, 2 to power 2 would be with that 2 zeros. 2 to power 1 would be 1 0, and 2 to power 0 is simply 1. And when you add all of them together, you would have 1 0, 1 0, 1. So there were 5 here, 4 there. Okay. So you would have, okay, maybe I should start from the right. So you add all of them up, you would have, okay. 1, 2, 3, 4, 5, 6, 7. And then the next number is 2, 3, 4, 5. And the next is 1, 2, 3, 4. And next is 100, next is 10, and then 1. And when you add all of them, you have 1, 1, 1, 0, 1, 1, 0, 1. So your representation is 1, 0, 1, 1, 0, 1, 1, 1 to the base 2. So this 183 is written as 1, 0, 1, 1, 0, 1, 1, 1 to the base 2. So, but this method is quite, look, soon there will be lots of bigger powers of 2 that we're dealing with, and it's sort of not that much practical to work with. So then what are the other ways that we can work on is that we can divide 183 by 2 and note down all the remainders. So what that means is, let me actually then move on to the, okay. Just 1 second. Is it stuck there? Right, it's not going. Just okay. So in powers of 2, we have written this number like this. I haven't explained my second method yet, which I would do soon. But before that, if we can convert 212 to binary, maybe I leave that as an exercise to you using similar method. To be honest, what you can do, you can write that down as 128 plus 64, that would be 192 plus 16, that would be 208 plus 4. That will make 212, and you can write it down in terms of their binary. Yeah. So that would be your binary representation. So as I said, this method is a bit awkward to work with large numbers. So we try to work on the slightly different method, and that different method is you divide the number and write down all the quotient and remainders at each step until the quotient becomes 0. So how we do that? So we have 183, and what we're going to do, we divide with 2. So 183 divided by 2 would be 91, and your remainder is 1. Then 91 divided by 2 is 45, and your remainder is 1. 45 divided by 2 is 22, and your remainder is 1. 22 divided by 2 is 11, and remainder is 0. Similarly, 11 divided by 2 is 5, and remainder is 1. 5 divided by 2 is 2, remainder is 1. And then 2 divided by 2 is 1, and remainder is 0. All right? So then this means your number that you're going to write would be, after 1, you cannot divide further. So you would have this 1, 0. So you will go all the way from here. So you would have then this 1, 0, 1, 1. So your representation would be similar, simply write that in reverse order. So 1, this one first here, then 0, and then this 1. So you're reading from tail to the head of this arrow. So, and listing all of them, and that would be your representation for 183. Now, if you have a number like 212 and you want to divide with 2, so you divide it by 2, you will get 106. It's exact division. The remainder is 0. Then again, you divide with 2, you got 53, and your remainder is 0. Then again, you divide it, it's 26. 26 times 2 is 52, your remainder is 1. Then 13, your remainder is 0. Then 6, remainder is 1. 3, remainder is 0. And that is 1 times goes in there, and your remainder is 1. So if you list them, 212 would be equals to 110, 10, 100 to the base 2. So just write down all of these numbers in this format. So you have 1, then 0, then 1, then 0, then 1, and 0, 0. That will be your base 2 expansion of 212. Right? Any questions, anyone?
Does that method have a name or anything?
Oh, it's just a division. Successive division by 2. Any other questions? Anyone? So what we did today, we introduced, we recall what are usual numbers that we deal with. These are real numbers, rationals and irrationals. We try to understand what are rational and what are irrational. And then we looked at we recall that, okay, any real number that you have, a number that you deal with in daily life has a place value, like 6,245.37. So there are 6,000s, 200s, 4 tens, 5 units, so on. So those numbers, we call those numbers as decimals. They have 10 digits in them. We said, okay, look, we dealt with then the smaller numbers, like the numbers in base 2, which are like only zeros and 1. We call them as binary numbers. Okay, and each digit of those binaries is called bits. 0, 1, in other words, on, off, true, false, and all that. So there are only 2 options we have. So any real number that you come across, you can actually convert that real number into binary. We started off with an example of, okay, we start with the integers like 183. We converted that into binary. How do we do that? We divide successively by 2 and note down all the remainders. And those remainders from bottom to the top, if we list them together, that would be the binary expansion of integers. However, you can also write them into 2 to the powers, like in the place value that you did if you want. But that way of working is slightly awkward, because you have to deal with lots of powers of 2s. We converted binaries when they're decimals as well into real numbers. Fine, we can do that. However, so far we haven't learned a method where you have like 22.37 and we want to convert that into binary. This would be the scope of next lecture. So in the next lecture, we'll learn again. We'll go over again how to convert integers into binary, and then we will convert any real number, like which may have some fractions in it, into binary. Okay, that's what we do next time. Should you have any questions, any stage, write an email to me, and I'll be happy to answer those questions straight away. Just feel free to book an appointment if you like anytime. Okay, what happened? Yeah, so I'll be happy to have consultation anytime that you want. However, there are 2 fixed slots where I would be available for you, and those fixed slots are, where I put them, those are Wednesday 11 to 12 and Friday 9 to 10. Okay. All right, so if there are no questions, I would say goodbye now, and I will see you on Friday at 11 o'clock. Same link, same password. Yeah, and until then, see you everywhere. Cheers. You're welcome.
Thank you.
Cheers, Mumtaz.
Thank
See
you.
Thank you.
Welcome.
Thanks, Montez.
Welcome.
Cheers, mate.
See you, everyone.